Welcome to Knowledge Share channel. In this video we will be discussing about DC machines, okay, regarding its construction and how it works, and also finally we will be deriving the EMF equation for the DC machines, okay. So only about the DC machines we will be discussing in this video. So regarding its construction, working, and finally we will be deriving one EMF equation, and also we will solve one problem, okay, based on the EMF equation. For example, for a generator, or if it is rotating at this particular speed, so what is the EMF that can be generated? So this is what the final agenda for this particular video, okay. So a detailed thing is, so here what is a DC machine? Okay, so DC machine, for example, it can be a DC motor or it can be a DC generator. Okay, a DC machine can operate as a DC generator or a DC motor. That is, the same construction can be made to operate as a generator or motor. Okay, the construction of both DC generator and motor are same or similar. That's what. Okay, for example, what is the difference between a DC generator and DC motor is, if I am giving the mechanical input to the DC machine, mechanical input in the sense I am going to rotate that armature, okay, I will tell you what is that armature, something I am going to rotate, okay, that if I am going to rotate the armature, then it will generate the electricity, or the mechanical energy will be converted to electrical energy. If the same DC machine, how it can be used as motor is, for example, if I am giving the electric current to that particular DC machine, it will start rotating. So the electrical energy is converted into a rotating torque, is it right? So that can be used in pumps and various other applications. So this is the basic difference between a generator, a DC generator, and DC motor. So both the DC generator and DC motor has the same construction or similar construction. Only thing is whether we want to give whether we are giving the electrical input, it will behave as a motor. If we are giving the mechanical input, it will behave as a generator and it will produce the mechanical output. So this is all the basics. So we have seen the many of the videos, you can see all those things, okay. So basically, what is an electrical generator? So generator is a DC generator is a rotating machine which converts the mechanical energy to an electrical energy. And why we want to convert the mechanical energy to electrical? Because we need electricity. So the electricity is being generated from the DC generator. Okay, so only in DC generator, the mechanical energy which we give, for example, if we are rotating the armature, it will convert it into the electrical energy. So how it converts? It is converted by means of the principle of electromagnetic induction principle. Okay, so that principle is called as the Faraday's law of electromagnetic induction principle. So what it states actually? So whenever a conductor moves in a magnetic field, so now we are discussing about the generator, please remember. So Faraday's law of electromagnetic induction is nothing but it is for generator, okay. So whenever a conductor moves in a magnetic field, a conductor is moving in a magnetic field, please assume that a conductor is moving in a magnetic field, what happens is it will cut the magnetic field, and because of which an EMF, that is electromagnetic force, or it is also called as voltage, an EMF or voltage is produced in the conductor. And if an external load is connected to that particular conductor, what is going to happen is the EMF will generate a current that will flow through the loop, that will flow through the external load. So this is how the generator works. For example, if you have only one conductor, a very less amount of EMF is only being generated, okay. So that's the mechanical energy. That is, what is mechanical energy? I am just going to move the conductor in a magnetic field. That is a mechanical energy I am going to give. That has been converted to electrical energy by inducing an EMF in that particular conductor. And if I connect an external load, you can see that that particular conductor will be delivering the current to that particular external load. So the mechanical energy is being converted to electrical energy in case of the generator. So if I use only one conductor, only a very less EMF will be generated, okay. So in order to produce more EMF, so we need around 230 volt or 240 volt or even 11 kilovolt or something like that. How that much voltage has to be generated, then we have to have more number of conductors connected in some pattern, okay, that is called as winding. Okay, the connected, all the conductors will be connected in one pattern. That pattern is called as winding. So there are two types of winding. One is called as a lap winding, the other one is called as the wave winding. So in a generator, you will be having a field pole. A pole will be there which will be producing the magnetic field, and an armature will be there which will be rotating in the magnetic field, and because of which the armature conductors will be cutting the magnetic field. The EMF will be generated in all the conductors, and the collective EMF will be very high because more number of armature conductors are connected to form a winding. So there are two types of winding. One is called as the lap winding, the other one is called as the wave winding. So lap winding is used for low voltage application with high current application, whereas wave winding will be used for high voltage applications and low current applications. So this is what is general distinguish difference between the lap winding and wave winding, which will be detailed we will be studying later. Okay. So hope you are all clear what is all about. Okay. So here in this video we will be studying Faraday's law of electromagnetic induction has been done, and how the EMF is being generated, and how the current flow. Okay, so the principle is O. So now we will move on with the construction. Okay, so in case of construction, what are the different elements that are present in a DC machine is like, the first one is it consists of frame, or it is also called as yoke. Why it is called as yoke? Because what is yoke? Somewhere you have heard this name yoke. In egg, is it right? So in egg there is a shell outside, that shell is called as yolk, is it right? So what is the use of this yolk? Actually it is going to protect the inner that is the inner parts. Yeah, the yolk is just going to protect the inner parts. Yolk will be very mechanically highly strengthened part, so because of which it will avoid any damaging of the internal parts. So yolk is going to protect. Okay, so we will see what are the functions of yoke later on. So it is having a yoke. So on the inner periphery of the yoke, you will be having the pole core. Okay, pole core is, we will be fixing the pole core, and pole shoes will be there which is fixed to pole core, and windings will be there, pole windings. So on the pole core you will be having the windings. Why we are using windings is because normally in case of DC generator we will not be using the permanent magnet, we will be using the electromagnet. So if we pass the electric current in the pole core through the windings which is placed in the pole core, that it will make that pole core as a electromagnet. Okay, it will make the pole core as an electromagnet. So that is what the principle. And finally interpoles is also there. What is the use of interpole we will study. Okay, and also we will discuss about armature core. What is this? So as I already told, what is armature? Armature is nothing but collection of conductors which are connected in series in parallel combination. That is called as armature winding. So armature core is the one which is going to carry the armature winding. Okay, so all the conductors, armature conductors are placed on the core. Okay, so there are two types of winding. One is called as lap winding and wave winding. So because of this armature and main magnetic field, because armature is also carrying some current, so because of which the armature also will produce a magnetic field. So this armature magnetic field will be interacting with the main magnetic field, and because of which the magnetic field, the resultant magnetic field will be quite distorted, and this is called as the armature reaction. This effect is called as the armature reaction. Okay, this effect is called as the armature reaction. Again we will be discussing about the commutator. What is the use of this commutator? Because the EMF that is generated is AC. So but the external, what is a DC generator? It has to produce DC. So this commutator makes the internal AC EMF to an external DC voltage. And finally the brushes and bearings. What is the use of brushes and bearings? So brushes are nothing but it is going to collect the current from commutator and it will be giving to the load. Whereas bearings are nothing but which is used for smooth rotation. There are different types of bearing which we will be learning later on, and bearings are used for smooth rotation without any noise and other things. And finally we will be, in this video we will be deriving the EMF equation of the DC machine, and also one small problem can be discussed. Okay, so this is what the final agenda of the entire video is all about. So this is how the construction looks like. So you can see that this is the construction of the DC machine. So suppose if you want a lesser, some easy view, so this can be used. Okay, for exams you can use this particular diagram, but for understanding you can use this elaborate diagram. Okay, so going into the construction, so you can see the frame, okay. So, you can see frame, where is the frame? So, here this is the frame actually, okay. I will just mark the frame. So, this is the frame. See, here it has been marked, yoke, okay. What is this yoke? Okay. So, here the yoke has two purposes. It acts as a protecting cover and it provides a mechanical support to the entire pole structure inside it as well. It also carries the magnetic flux produced by the poles. Okay, that is, the poles will be producing the magnetic flux and that magnetic flux will be passing through this yoke only. Okay, so this particular frame or yoke, it can be made of two different materials. One is cast iron, the other one is cast steel. In some machines it is made of, this yoke is made up of cast iron. In some machines it is made up of cast steel. So, cast iron is very cheap, the cost is very less, but the weight is little bit high, and because of which the cast iron is restricted only for small machines, whereas cast steel, it is very costly, but its weight is very less and it can be used in large machines because it has high permittivity, and because of which the weight is reduced and the flux path is very easy. So, flux losses will be less in case of the cast steel when compared to cast iron. So, these are all the things which you want to understand from the yoke. So, yoke is nothing but mechanical support is provided by the yoke, as well it carries the magnetic flux. So, two different types, cast iron and cast steel. Okay. So, cast steel is the best one, but it is highly costly. So, next is poles. So, what is pole? So, here you can see that this is pole. So, I will just mark it. You can just see the pole, which is pole. So, here this is the pole. This I am just marking in the brown color. So, this is the pole. It is, you can see that the pole is in the inner periphery. It is in the inner periphery of the yoke. Okay. It is in the inner periphery of the yoke. So, here you can see that. So, this is the pole shoe. So, here why this, you can see that the pole shoe is quite elongated. So, this is done in order to have the uniform air gap, and this is called as pole core. You can see the pole core. So, pole core is on top. So, this is the top one is the pole core, this one, okay, and this one is the pole shoe, this one. So, it looks like shoe. So, something with the shape of shoe. So, this is called as, I will just mark, which is pole shoe. So, I will just mark in green. So, here this is the pole shoe, this one, okay. This one is the pole shoe, and the above brown color is the pole core. So, hope you are all clear with the pole. So, what is the use of this pole? This pole is going to generate the magnetic field. So, you can see that around the pole core, you can see that some winding is there. You can see here, in all the pole core you can see the winding. So, this winding, that is field winding, it is called as a field winding, okay. So, it is called as field winding. So, a pole is having, so why we are using this pole is because winding is because when we pass the electric current through this winding, this particular pole will be converted into an electromagnet. It will be converted into electromagnet. So, your pole will be having a pole core, a pole shoe, and it is having a pole coil. So, this is the pole. Pole is nothing but it is used to generate the magnetic field. See, whenever a machine will be operating only in the magnetic field. A magnetic field has to be produced. Okay. So, as we have discussed, the pole shoes is quite elongated in order to reduce the air gap reluctance and to increase the area so that the flux is uniformly distributed. So, the poles are nothing but electromagnets, and the field winding is wound over the pole core, okay, and the pole coils are made up of copper wire, please understand. So, when the current is passed through this pole coils, the poles will become electromagnet. So, the magnetic field is produced inside the machine. Okay. And these poles, you can see that these poles are laminated. What is it laminated? It will be sliced actually. It will be sliced and then bolted together to form a single core. So, why it is being sliced and some insulation will be placed in between. Why it is being sliced is in order to reduce the eddy current loss. So, whenever the magnetic field is there, the magnetic field will be creating some losses in the pole core also. For that also, the electricity will be taken from the generator itself. So, the losses will be high. So, the whatever electrical energy that is produced, the delivery part to the load will be reduced if the losses is high. So, in order to reduce the losses, we will be always laminating the pole core as well as armature core is also laminated. Okay, we will see it later. So, it is laminated. Okay, and in order to reduce the eddy current loss, please understand this pole cores and armature core, everything is laminated. Laminated means it has been sliced, and in between each and every slice, for example, 0.5 millimeter thickness. So, each and every slice will be only 0.5 millimeter thickness, and in between each and every slice you will be having some mica insulation sheet in order to prevent this eddy currents flowing inside the core, and so that the eddy current losses will be minimized. So, this is what all about pole core. Okay. So, now let us move to interpoles. So, I think the interpoles will be the next thing. You can see that this is one more representation. So, here also you will having something, you can see that. So, this is the field pole. Okay, so this is the pole core, and this is the pole shoe. Okay, so this is the pole shoe. I will just mark in violet. Okay, this is the pole shoe. So, pole shoe and pole core, and this is the winding. So, winding I will just draw. So, here you can see this is the winding. Okay. So, each and every machine will be having all these things. Okay. So, here how many number of poles are there? 1, 2, 3, 4. 4 poles are there. So, the poles should be of even numbers. Okay, in order to generate uniform air gap. Okay. So, here you can see that something in between. So, I will just draw. Okay. So, this is pole core. Then what is this actually? You can see that see here one pole is there. Here also one pole is there. Here also you can see one pole is there. Here also one pole is there. So, totally 4 interpoles are there. So, 4 normal poles are there and 4 interpoles are there. So, this is called as interpole. So, why this interpole? What is the use of this interpole? What is the use of this interpole? So, interpoles are used to improve the commutation process. I will tell you later what is that commutation. Okay, what do you mean by commutation? So, just understand that this interpole is used to improve the commutation process, because this interpole windings. So, these interpoles will be having some windings which are connected in series with the armature, and because of which the armature reaction will be reduced. So, I will also tell you what is the armature reaction later on, and because of which the commutation will be improved. Okay. So, this is the function of interpole. So, this has been asked in many of the question paper. So, each and every pole will be accompanied by in between 2 poles you will be having an interpole. In between 2 poles you will be having an interpole. So, if you have 4 poles you will be having 4 interpoles. So, the interpoles are used, will be connected in series with the armature winding. Okay. So, this is the armature which is at the center. I will just mark it here. So, this is the armature. Okay. So, this is all these 4 interpoles will be having the windings which are connected in series with the armature winding. So, you know that reaction called as armature reaction will be taking place, which will reduce the magnetic flux actually, which will be dealing with later. So, this interpoles, what it does is it will reduce the armature reaction effect, and because of which the flux will be improved. Okay, so only when the flux is improved, the torque will be good and the machine will generate maximum energy. If the flux is getting reduced, then the energy generated by the machine, the electrical energy generated by the machine will be less. So, in order to improve the electrical energy output, you are using these interpoles. So, hope you are all clear the difference between the interpole and normal pole, and this is the armature which is placed in the center, and the armature is going to rotate, whereas the field poles and interpoles are all stationary elements. Okay. So, now going back to this, or okay, we will start with this. Okay. So, you can see that armature. So, now we will move on with the armature. So, we have discussed about we have discussed about yoke, we have discussed about poles, and we have discussed about interpoles. So, now we will be discussing about armature. So, what do you mean by armature? So, you know that armature is the one which is going to rotate. You can see that. So, this is the armature. I will just mark it here. So this is the armature which is placed in the center. So it will be having the armature conductors will be there. So as I have told, if we have only one conductor and only one conductor is going to cut the magnetic field, an EMF will be generated. But that EMF will not be sufficient in order to drive a load. It will be generating only about 1 volt or something like that. So in order to have 230 volt, you need 230 conductors which has to be connected in series and parallel connection. That forms the winding. So that is called as armature winding. If you place only one conductor, it is called as conductor. If more conductors are connected in series and parallel combination, it is called as winding. So as I have already told, there are two types of winding. One is called as a lap winding. The other one is called as a wave winding. Okay, lap winding is used for high current application, whereas wave winding is used for high voltage applications. So in detail we will study later. Okay, so this is called as armature. Okay. So the armature is going to rotate inside the magnetic field, and since it cuts the magnetic field, an EMF will be generated in each and every conductor, and that EMF is the cause for the current flow in the external load. Hope you are all clear. Okay. So what happens is the armature windings which is placed in the armature core, okay, will be rotating under the poles, and hence the flux produced by the field are cut by the armature conductors. And also you should note that some eddy currents also will be produced inside the armature. Why these eddy currents are produced is because this armature is also carrying a current. So because of which the armature also become an electromagnet, and because of which some currents will be flowing inside the armature core itself. So this will lead to loss of many a huge energy inside the armature core, which will not do any useful work. It will just overheat the armature and it will reduce the efficiency. So in order to improve the efficiency, we have to reduce the eddy current losses inside the armature. So it can be reduced by laminating the armature core. How to laminate? You just slice. So it is not a single core. It is nothing but a combination of more number of steel structures which are having insulated parts in between, insulated mica in between, and then it will be it will be stacked. It will be stacked in the sense it will be stacked with the help of bolts and nuts, and it will be made as a single core. So by doing so, what we are going to achieve is the eddy current losses will be reduced. So since the eddy current losses are reduced, the efficiency will be good because of less power loss. Okay. So the laminations will be only of about 0.5 mm thick. Okay. So now you are clear with what is an armature. Okay. So now you can see, so this is the armature conductor. So now you can see something called as commutator. Okay. So we will, so anyway, this is, you can see that the armature windings, everything is connected to somewhere here. See here it has been connected, see here it has been connected. So this is your commutator actually, this particular part, the central portion, the in-depth portion. So this is your armature. So I will draw here. So this is, I will draw in violet. So this is your armature conductor, and the violet color is the armature conductor. And this green color is your commutator. The commutator, okay, the commutator is at the center of the machine. So what is the use of this commutator? As we have already discussed, this commutator is going to convert the AC EMF which is generated inside the machine, and it will be converted to DC EMF. So it is made up of many segments. You can see that many segments are there, and each and every segment will be insulated by mica. And it will be cylindrical in shape. Okay, so the armature coils are soldered to the commutator segment by means of a component called as riser. Okay, please understand. Okay, now what is meant by then we will move on with the brushes. Okay, now we will move on with the brushes. So I don't know whether it is clear here. Okay, so we'll move on. Okay, so here in the next thing you can see more clearly. You can see have a very good understanding of how this commutator works. So here you can see this is the armature conductor. Okay, this is the armature conductor, and I will draw it in green. So this is your commutator. So this commutator will be of cylindrical in nature, and you can see that the armature winding is connected to the commutator segments. Okay. So how this segment operates is, so here you can see that inside the machine you will be having an AC. What is AC? You will be having a positive cycle as well as a negative cycle. Whereas here you will be having, how this commutator operates is, for example, if you have a coil ABCD, so you are having a coil ABCD, okay, some coil is there, something, okay. What happens is the coil, if it is in parallel with respect to magnetic field, no EMF will be generated, so because no flux will be cutting, is it right? So here you can see maybe this will be more clarity. So here you can see that ABCD is there, okay. So here I will explain, okay, about the commutator later. So here you are having A, B and C and D is there. So if it is in perpendicular direction, you can see that, so only when the knife is in perpendicular direction, it can cut maximum. Similarly, only when the armature conductors are in vertical position, it will cut the magnetic flux to the maximum. So because of which high EMF will be generated in that particular conductors. So for example, if the armature conductors are in flat position, something like that, or if it is parallel, okay, so here you can see in the second, okay, in the second thing, this one, okay, in the second thing. So this is first thing where it is perpendicular. So here it is flat, you can see that it is parallel. So it is parallel. So because of which what is going to happen is the EMF generated will be minimum or 0. So you can see that as this armature is rotating, as the armature coil rotates for one revolution, then one cycle of sine wave form will be produced. So if the coil is connected to the slip rings, then the AC EMF only will be produced. So because of which, but we need, as a DC generator, it has to produce DC output. So we need a component called as split rings, and this split rings is called as a commutator. A split ring is nothing but initially it is having two segments. So here you can see, so this is your commutator, so this is your commutator, okay. So it is having two segments which are insulated from each other by means of mica, okay. One is segment A, the other one is segment B, okay. So, so what it does is actually, these two segments, what it does is, so for example, when coil AB is connected, then P segment will be connected, whereas when coil CD is connected, the Q segment will always be connected. So the brushes B1 and B2 always, okay, it will touch the P and Q in order to collect the current. So the first half of the revolution, the current flow will be from, like, you know, AB LMCD. The current flow will be from AB LMCD, okay. And whereas in the, for example, when you go with the next half cycle, that is during the negative half cycle, in this cycle, okay, in this cycle you can see that again it will be, the current flow will be in the same direction. So here also the current flow remains the same direction, here also the current flow remains the same direction, and this results in this particular output wave shape. That is, since the load circuit will be having the same direction in both positive and negative cycles, so the negative cycle will be converted to positive cycle. So this is nothing but your DC, is it right? So this is nothing but your DC. A DC is nothing but a waveform that is having unidirectional direction, that is called as DC. So this is your DC. So this is how this particular split ring is going to convert the internal AC EMF to external DC EMF. Is it okay? Okay, hope you are clear. So now finally we will close with brushes. Okay, so what is the use of this brush? So here you can see that some brushes are there. Yeah, so from the commutator you can see that two brushes are there. Is it right? So two brushes are there. So you can see that the commutator also will be rotating along with the armature, okay, but whereas the brushes will be always idle, it will not rotate. The brushes will never rotate, okay. So these brushes are made up of carbon or it is made up of graphite. You may ask one question, why it is made up of carbon? Because carbon, it is having a good, good life, okay. It is having good life, and also the resistance of the carbon material is quite less, because the carbon brushes has to collect the current, which should have very less resistance. So carbon brushes are having very less resistance if you have good area, and because of which the carbon brushes are used in order to collect the current from the commutator, and that is given to the external load resistance. So the brushes are placed in the brush holders. So, for example, and also there are bearings will be used, okay, the bearings will be there inside the, so there are two types of bearing, one is a ball bearing and roller bearings will be used. Ball bearings are used for small machines, whereas roller bearings are used for larger machines. And what is the use of this bearing is only if you use bearings, so because while rotating, some noise will be there. In order to reduce the noise, this bearings will produce a smooth operation, and so the noise will be quite reduced. So that is the advantage of this bearing. So in almost all the machines, the bearings will be used. So hope you're all clear. Okay, so this is how the commutator works, and this is the actual diagram of your DC machine. So it is having a yoke, it is having a field pole with field winding and pole shoe, armature core and armature winding, and commutator is there. Okay, split ring is there, and finally the brushes are there in order to collect. So these are all the operation of the. So finally we will discuss about how the windings of the armature is there. So it can be a single turn, it can be a two turn, or it can be multi-turn. So these are the different types of windings of the armature coils. So depending on our requirement, for example, if the power requirement is very high, we have to go with the multi-turn. If the power requirement is very less, then we can go with a single turn. So according to our requirement, we can choose which type of turn will be suitable for our application. Okay. So and one more thing is, there are two, as I've already told, there are two types of winding. One is called as a lap winding, the other one is called as a wave winding. So in case of lap winding, you can see that, what is happening in lap winding. Okay. See, in lap winding, what is going to happen is, this is the start of the coil. Okay, the start of the coil is connected, to the end of the coil, and this end of the coil is connected to the start of the next coil. So you can see that the end of the first coil is connected to the start of the next coil. So this is the first coil and this is the second coil. So the end of the first coil. So here you can see that this is the end. Okay. So this is the end of the first coil is connected to the start of the second coil. Similarly, the end of the second coil, you can see, so this is the end of the second coil, again it is connected to the start of the first coil. So this will be continuing, and this type of winding is called as a lap winding. Whereas in case of wave winding, you can see that the end of the first coil, you can see it is not connected to the start of the second coil, whereas it is connected somewhere at some distance away from that particular coil. So this type of winding is called as a wave winding, lap winding. So both are having some plus and minus. Okay. For example, lap winding is suitable for high current application, whereas wave winding is suitable for high voltage application. The only thing is which you want to remember is, this is the very important thing which is used in all the problems. For example, if the generator is given as wave winding, then you have to take the number of parallel paths as 2. If the generator is given as lap winding, then you can take the number of parallel paths as number of poles. So these are all some of the differences, like number of brushes are equal to the number of poles in case of the lap winding, whereas number of brushes will be less. Only 2 number of brushes are required for wave winding. Okay. So this distinguish between lap winding and wave winding has been asked in many of the question papers. So preferably for high current and low voltage applications, this lap winding is suitable, whereas high voltage, you can see that for high voltage applications, this wave winding is used, whereas high current applications, lap winding is used. Okay. So more than 500 amps, you can see, so this particular lap winding is used, whereas less than 500 amps, you can see that this wave winding is used. So this is all about lap and wave winding. Okay, hope you're all clear. And now we will discuss about what is the EMF equation. So this is all about the construction is over. So now what is EMF? So EMF equation is a very simple equation. So finally you will be deriving an expression. What will be the EMF generated? So there should be some equation, is it right? So from that equation you can just substitute the values and you have to find the EMF generated is this particular value. So mathematically you can calculate. So let us assume that P will be equal to number of poles, phi equal to number flux, whereas N is the speed of the RPM, and Z equal to number of armature conductors, and A is nothing but number of parallel paths. So A will be equal to P where in case of lap winding, because number of parallel paths will be equal to number of poles, whereas A will be equal to 2 in case of the wave winding. Please remember it. Okay. So you can see that the induced EMF, according to the Faraday's law of electromagnetic induction, everybody knows that induced EMF will be equal to d phi by dt. What is this d phi by dt? Rate of change of flux with respect to time. So this is called as, so this is the EMF which is being generated. But you know that we don't use, because we are going to consider for one full revolution. So in one revolution, the conductor will cut about 5 into p number of poles. So this much number of poles will be cutting in one revolution, and also it will take around 60 by n seconds in order to complete one revolutions. Okay, so from this you can see that 5p is nothing but so 5 into p is nothing but your d phi. 60 by n is nothing but dt. So you just substitute and finally you will be getting a formula something like E. So this is only for one conductor. This we have to remember, it is only for one conductor, but we are using Z number of conductors. Yeah, so the Z is nothing but the total number of conductors. We are not using only one conductor, so totally Z number of conductors are used. Okay. Okay, so now we will move on. Okay, so you can see that so since the Z conductors are used, okay, with A parallel path, so the total number of conductors is Z by A. So finally the expression comes something like this. Okay, that is sorry. So finally expression comes like this, that is the EMF generated will be equal to phi Z. Okay, that is phi P N Z divided by 60A. Or in short, I will always remember in I will tell like phi Z and P, phi Z and P. Okay, 5 ZnP by 60A. This is what the formula of the. So in case of lap winding, this particular A. So here the 5 ZnP by 60A is there. A will be equal to P for if it is lap winding. A will be equal to 2 for if it is wave winding. This is what you want to remember. So we will just solve one problem. So this is the problem which I am going to explain to you now. Okay. So this problem, okay, this is a sample problem, many sample problems are there. So here you can see that a generator is having a 4-pole and it is running at 1500 rpm and it is lap winding. So this is very, very important, and it is having 24 slots and it is having 10 conductors per slot. So the flux produced is 0.04 Webers, and we have to calculate what is the EMF generated by the armature and what would be the EMF generated if it is wave connected. So you can see that. So these are all the questions that has been asked. So first you write the given data. So number of poles is P equal to 4, N equal to 1500 rpm. So lap, that is A equal to P. So phi is given as 0.04 Weber. So what is Z? Z is nothing but number of slots and number of conductors plus slots. So 24 into 10, which is nothing but 240. So finally you just substitute here phi Z and P by 60A. So A is nothing but the number of poles, that is number of poles is number 4. So I am going to substitute here 4, and finally I will be getting the generated EMF is 240 volt. So suppose if it is a wave connected, then you will see that A equal to 2. So here you can see that A equal to 2, whereas in lap winding it was A equal to P. Is it right? So here in A equal to P was there, here A equal to 2. So again you can see that A equal to 2 is substituted. So phi ZnP by 60A. So A is 2. So you can see that it is generating 480 volts. So from this problem we can understand that a wave generator, the same machine, if it is wave connected, it can generate high voltage of about 480 volt. You can see that double the voltage has been generated, whereas if it is lap winding, it will generate 240 volt. Okay. So but lap winding is having the advantage that it can carry high currents. So lap winding is used for high current application, whereas wave winding is used for high voltage applications. So that's all for now. So in this video we have discussed about the construction of DC machine. We have discussed about the armature, poles, yoke, and also we have discussed about the commutator, brushes and all those things. And we have discussed about the lap winding and wave winding, and in which application lap winding and wave winding can be used. And finally we have discussed the EMF equation derivation. And also we have discussed one problem based on that EMF equation, what will be the voltage that will be generated. And we have finally come to the conclusion of this video. So thank you very much, and if you really like this video, give a thumbs up, and as well if you have any doubts you can comment, and if you like this video to be shared with someone, you can just share. And also if you like the videos which I post on this channel, you can just subscribe, and you can support this channel. And thank you very much. Thank you.